a system in which energy is stored, the system which is not in its quiescent state, to which no excitations are applied, tends to its quiescent state, in which the energy is distributed over system parts, dissipated in system parts, or radiated by system parts. We are not so much worrying about what mechanism is behind, let's say, going to the quiescent state, but it's important that you understand that if there is energy, that is the physical meaning later on of poles and zeros, and that is also the idea how we are going to estimate them later. By having this physics in mind. So for example, if there is charge on the capacitor, it will, and there is no excitation, no signals, no voltage or current sources applied to the network, then maybe the charge will flow away over and dissipate. The energy will be dissipated in a resistor, and after some time, there's nothing left of that charge. And this process of describing this, that is what we are going to deal with today. If excitations are applied to such systems, the responses, so the output signal, logically now must depend on the energy stored in the past. So if the energy is not yet distributed and the system is not in its quiescent state, then there's still something left. And of course, the current values of the excitations. Systems like this are called dynamic systems. So the definition of a dynamic system you find in the, I think it's chapter 15 or 16, a system in which the responses are not only on a time instant t, are not only defined by the excitations of the time instant t, but also on previous values of the excitations, or on future values, but we don't have those systems yet. So we call them causal, and we only have the past to deal with. Now, how do we describe such linear or linearized time-invariant dynamic systems? We model them with linear differential equations with constant coefficients. If the coefficients are not constant, depend on time, then probably the system is time variant instead of time invariant. And if the differential equations also hold excitations and responses to higher orders than one, then it is probably a nonlinear system. So how does such a differential equation look? A sum of a number of derivatives of the response is equal to the sum of a number of derivatives of the excitation. So it's first nice to understand the sentence and then to write it down in the language that we usually use, which is mathematics. So here you see if the response is yt and the excitation is xt, then a sum of a number of derivatives of yt equals a sum of derivatives of xt. The nice thing to know about these differential equations is that exponential functions retain their shape under differentiation and integration. So if we are able to write a signal as a sum of exponential signals, as a linear combination of exponential signals, then it's easy to solve this differential equation, because then the shape of all the signals is the same and only the coefficients are going to change, because that is what happened if you take a derivative of an exponential function. And that is basically what Fourier and Laplace did. Fourier says write the signal as a sum of imaginary exponentials. And that is only possible if signals have finite energy. And there are also other conditions, but that's why you have mathematics as well. So we don't deal with it here. And this is how what you have learned as the inverse Fourier transform, but basically it is really what is happening. It is writing xt as an infinite sum of exponential imaginary exponentials. And what we usually call the Fourier transform, which is this capital Xg omega, this one is the Fourier transform of xt, and we find it from correlation, and it is the complex amplitude of an exponential. That is what it basically is. So the Fourier transform of xt. Unfortunately, if we can only use Fourier for finite energy signals, then in an unstable system, the energy is unbounded, theoretically, of course, because in practice it will always be bounded, but then it will not be linear anymore. So theoretically, in a perfectly linear system, but unstable, the definition of an unstable system is that the response to a bounded excitation is not bounded, which means we cannot deal with Fourier then. There does not exist a Fourier transform of such a signal. And then we have the Laplace. It writes the signal as a sum of complex exponential, not imaginary, but complex. And this can be used for power signals as well. And here is what you have learned as the inverse Laplace transform. The time function is written as an infinite sum of complex exponentials, st, times some factor, and this factor is called the Laplace transform. It's basically the complex amplitude of such an exponential. So we call x as the Laplace transform. It is the complex amplitude of the complex exponential, and it is the Laplace transform of xt. That is, I think, that you are familiar with. You should be familiar with. And by working with this exponential, with these transformations, with this Laplace and Fourier transformation, we can solve differential equations because those exponential functions retain their shape. They drop out of the equation, and your equation changes from a differential equation into an algebraic equation. And then we can define a transfer function, which relates the response of each exponential to the excitation of the corresponding exponential. So, in Fourier terms, hg omega relates yg omega, the response, to xg omega. And the transformation of the differential equation shows us that this must be the expression, the sum of these coefficients of the numerator and the denominator. For the Laplace, it is the same, only g omega is s and g is a complex variable.